All right, welcome everybody to our lecture series today. It's a pleasure to have Bill Freeman here. Bill is a professor at the MIT in the Electrical Engineering Computer Science department. He's a member of the Computer Science and Artificial Intelligence Lab. And since 2015, he's also been a research manager at Google Research in Cambridge. Of course, many people know that, well, many of the works that Bill has been doing. And Bill is a pioneer in computer vision. He's published many papers. He's been awarded many times. He has been outstanding papers in computer vision and machine learning in 97, 2006, 2009, 2012, 2019. He has Test of Time awards for many papers for in 1990, 1995, 2005, and so on. And he's been, of course, well known, and it's really great to see his passion for research when you listen to his talks, but also when you see his new papers that are often like spanning across the fields. It's really an inspiration for many researchers to see how we can apply computer vision, machine learning techniques in various different areas. And one example was, of course, the Event Horizon telescope, which has received so much great press, and it was really fantastic to see this coming out also from his lab. So today he's going to talk about the moon camera, and without further ado, Bill, you have the stage.
Okay, thanks so much for the introduction. I'm really sorry I can't be there with all of you. It's so much easier and nicer and more fun to be in person, but I'm glad to be there with you anyway. Those of you who are willing, I find it much easier to give a talk if I can see you. And so you don't have to if you don't want to show yourself, but if you're willing to show yourself, it'll just make it easier for me to give the talk. Thanks for considering it. Okay, so this is kind of a research saga talk, and it's something I'm passionate about, and I want to share it with you. So here's the full title of my talk. It's like this Dickens length thing: The Moon Camera: My Attempts to Photograph the Earth from Space Using the Moon as a Camera, and Several Computational Imaging Projects Resulting from Those Attempts. Okay, now, I work at both MIT and Google, and it's almost as if I can't decide whether I want to be in industry or in academia. I've spent actually half of my career working in industrial research labs, and half of my career working at MIT, and now I work at both. But even though I can't decide which is a better job, I do know for sure the one job that's just absolutely the best, and that is to be an academic researcher while on sabbatical. This is just a perfect job. It only lasts for a year. It's even better than not working, because you know that after this 1 year sabbatical ends, you're gonna have to work really hard. And anyway, it's a very special time. So in 2008, I was on sabbatical, and I spent most of that year looking around at different things in my world and asking, can I make a camera out of that? Can I make a camera out of that? Can I make a camera out of that? And I looked up at the moon and I asked, can I make a camera out of that? And somehow I just got infected with that problem. It just stuck with me. And I thought about it for a long time, and I've been working on it off and on, slowly, not full time, for 12 years. And so I want to tell you about some of my efforts to work on this problem and various sort of computational imaging spin-offs that have resulted from it. So what's the story here? Well, here's the moon, and there's the sunlit part of the moon. This is kind of overexposure, so that part's really very bright. That's the sliver that you would see prominently. And then over here, this is the dark side of the moon, but we can see it there. We can see it lit up. Well, what's going on there? It's not lit up by the sun, but we can still see it. What's the light source that's lighting it up? Well, it's the Earth. It's lit up by reflected light from the Earth. Here's a not to scale picture showing what's going on. You got your sunlight there. It bounces on the Earth and then reflects off toward the moon, illuminating with what we call earth shine, which is analogous to the moonshine that we see at night. And so this earth shine lights up the dark part of the moon, and it reflects back and we can see it. So then this is the goal. We want to look somehow at that earth shine lit up by the Earth and somehow pull out an image of what the Earth looks like Earth would look like it if you were standing on the moon. Okay, now, I first have to address the question, why in the world would you want to do this? Okay, so there's two reasons why to do this. Okay, because I acknowledge just right off the bat, we have satellites, we can get pictures of the Earth from space by other means, and they're going to be much higher quality than what we can do this way. But why would you want to do it? Well, one, it would just be so cool. It would be so neat to have this picture that was taken from a ground-based photograph on the Earth, a picture of the Earth. And it's kind of like a conceptual art project, because it's not the image in itself that would be so neat. It's the idea behind the image, how the image was made, that would be really cool. So that's my motivator, my main motivator. And I would talk about this with people, and like I would call it the dark side of tenure. In other words, with tenure, you're allowed to work on whatever you want to work on. And this is the dark side, that someone would go off and just do this crazy project. And I told this to my department head, and he just really didn't like that characterization. He just thought it was somehow sacrilegious to imply that there was a dark side to tenure. But anyway, but then there's a second reason to do this project, and that is a science outreach reason. That I want to let amateur astronomers, backyard astronomers, go into their backyard. And currently they can go into the backyard, set up a camera and a telescope, and they can take pictures of Jupiter and their own pictures of Saturn. And it's pretty fun. Well, this would be discovering a new planet for backyard astronomers to photograph. They could photograph the Earth now. And perhaps they could look at large continents or large weather patterns. And it would, I think, it would promote computational imaging, promote astronomy, promote Earth science. I just think it would really be helpful for science outreach. And kind of an inspiration for that is this picture of the moon from Apollo 8 in the bottom right. And this photo really captured the world's imagination of seeing the Earth from a new perspective. And we couldn't possibly hope for the impact that this one picture has had, but we want to kind of move things in that direction. We hope that maybe it would get people thinking about Earth sciences more, about imaging more. So that's the second and perhaps primary reason for doing this project as science outreach. Okay, now, how hard is this problem? Okay, I have a little demonstration to show you how hard it is. If the Earth is the size of a quarter, how big is the moon? Well, the moon is the size of a pea, okay? Then how far apart are these two from each other? Well, looks about right here. No, it's not like this at all. It's actually arm's length. You can't see it there. They're arm's length away from each other. And so here's the task. You want to look at you're sitting on this quarter, you're looking at this P, which is right next to the camera, arm's length away. And you want to look at the light that this quarter shines on that P and somehow distinguish the effect of a ray of light coming from the top part of this quarter from a ray of light coming from the middle part of this quarter. You want them to have a visibly different effect on the image of the P, so that then you could look at the P from the Earth and compute, back out what an image of the Earth from the P would look like. And so you can see the angles involved are really, really small. There's only a very tiny angular difference between light coming from one part of this quarter versus light coming from another part of the quarter. So that's the task. And so you might imagine that the whole issue is going to revolve around resolution, like how finely can we observe different resolutions on the moon, and indeed that is so because we have this requirement that we want it to work for backyard astronomers, we have a number of constraints on this task. One, we're going to use optical imaging. We're not going to use infrared. We're going to use visible band. And then the resolution requirements have to be what a backyard astronomer can resolve from their telescope in their backyard. So what are those limitations? Well, there's two things that limit the resolution you get in an image of the moon from the Earth. One of them is the diameter of your telescope. diffraction limits that. And then the other is turbulence in the atmosphere. And often it's turbulence that's the real limiter. So if you have good atmospheric viewing, typically you can get 1 arcsecond of resolution. Okay, so so the moon itself is half a degree as viewed from the Earth, and there are 60 arc minutes in a degree and 60 arc seconds in an arc minute. So that's 1,800 arc seconds as seen from the Earth is the whole moon, and you can get about 1 arc second of resolution on a good calm night looking from the Earth with about a 5-inch diameter telescope. Sorry for that. Sorry for those crazy units. But then there's one way to get around the atmospheric issues, and that's a thing called lucky imaging. So here's lucky imaging. You take 1,000 photographs of the thing you want to look at, each one very short. And during some of those exposures, the turbulent air is going to be calmer than during other times. And if you selectively find the images of your set of 1,000, which have slightly more resolution, and average those together, you can get a much better resolution than just by taking one shot alone. And so if you look at the blogs of what amateur astronomers can do, they can sometimes get down to 0.2 arc seconds of resolution, but that's like a really good amateur astronomer. So let's be a little bit conservative and say we're going to allow up to 0.5 arc seconds of resolution, which is using lucky imaging, and it requires a 10-inch diameter telescope. So that's kind of good backyard imaging. Now, if we're willing to allow ourselves to use a professional telescope, then we can get down to 0.2 or 0.1 arc seconds of resolution, and I'll show you the improvement that can bring. Okay. Now, so that's kind of the rules of what we're going to allow ourselves technically. Now let me tell you about the 3 different approaches I've tried to solving this problem. One is measuring diffuse reflections of Earth's shine from the moon. Another is observing fuzzy boundaries of cast shadows of Earth's shine. I'll talk about that. And then the third, I won't really have time to get into, but it's another way of doing it, measuring specular reflections of modulations within sunlight. And the kind of the overarching story is that no, I haven't done this. I haven't succeeded yet, but I've kind of outlined the limitations that we're close. And the cool thing is that each one of these methods has led to really nice spin-offs in my own research in computational imaging. So I want to tell you about those spin-offs. So it's kind of like a research saga story. Okay, diffuse reflections of Earth shine. So here's like the simplest approach you can imagine. We're going to assume the moon is a perfect sphere. It's a diffuse, perfectly smooth, uniformly colored sphere. And so that's the P there. And we want to figure out, if we look at that carefully, how can we make an image of the Earth? Now, I want to remind you of Bayes' rule. So let's say that X is the unknown Earth image we want to estimate, and Y are the observations of the moon that we're going to use to make that estimate. We can form a probability of any one Earth image being what's actually the true Earth image, and it's a product of the so-called likelihood term times this prior term. There's a linear relationship, as with all imaging systems really, between the brightness of a point of light on the Earth and the brightness that we measure looking from the Earth at the moon. And so that rendering matrix is A. So X is, say, a rasterized versions of all the points of light on the Earth. And then there's a transfer matrix A, and then the result is some kind of a brightness pattern on the moon. And if we assume that there's Gaussian observation noise in our observations, then we can have the likelihood term be have this Gaussian form. So this tells us for any given hypothesized Earth image how probable it was to have generated the data that we saw, and then we multiply by how probable it was all on its own to get the posterior probability. Okay, so what's the rendering of the moon like? The moon is a really rough surface. So here's some spheres. This is made by Sri Nair and collaborator. These are 3 different spheres. On the far left is a Lambertian sphere, and you can see it fall. It gets darker at the edges if you light it from the viewer's position. That's because the angle with respect to the surface goes down and it reflects less. But if you have a very, very rough sphere, then it becomes almost retro-reflective. And indeed, that's actually how the moon looks. So it's a very retro-reflective, very, very rough surface. And so so the BRDF, the bidirectional reflectance distribution function, is a 4D function for any given surface normal. You have the 2D description of the input light angle, and then the 2D description of the viewing angle. This is just a 1D slice of that function for both a Lambertian reflectance function on the moon and one particular model called the Miniart's model for the reflection on the moon. Each one of these tells the same story, though, which is that all the action is going to happen at the very edge of the moon, as seen from the Earth. And why is that? Again, we have our quarter, and we want to be able to distinguish a difference in the brightness that you see on the moon as a function of a very, very small difference in the angle, the incident angle of the light ray coming at the moon. And you can see from these curves that the only place where you get a quick change in intensity, so intensity is plotted vertically, the only place where there's a sudden change of intensity with respect to the input angle, and the input angle is plotted horizontally, is at the very edge of it. So even with Lambertian, there's a discontinuity there, a derivative discontinuity right at the edge. And with these other more retroreflective models, there's a very sudden fall off with respect to the edge. So the only place we have any hope of seeing a brightness change caused by these very, very small angular differences of the incoming light is at the very edge of the moon. And so that's where we're going to make our observations. We're going to make, say, 1,000 observations at these different points along the moon. So here's a picture of showing the curvature of the moon, and we're going to sample them equally in angle. And if we zoom in by a factor of 4 and zoom in by another factor of 4, we can see we're going to take 5 measurements of the intensities just at the very edge of the moon. Astronomers call that the limb of the moon. And that's the only place where we can hope to see an intensity difference caused by the brightnesses of the Earth over different parts of the Earth. Okay, so then we can study if this is feasible by forming this so-called transfer matrix. And here's a little picture of it. So here we have the Earth at the top right here. And we're going to take a raster scan viewing of the Earth. And so we're going to first look at this pixels. We're going to assume that we have a single point of light at all these different positions here. First on this raster line, then the next raster line, then the next raster line. And then if you assume you have a single point of light there, we're going to look at what is the brightness that you observe on the moon under the BRDF that I showed you in the previous slide. And we're going to plot out all those combinations as a big matrix. So for this first green line here, we're going to look at each of the measurements along the moon in this column. And so the red region here corresponds to the part of the moon very closest to the edge, and then the green is slightly further in from the edge, further in, further in. And so we plot all those intensities in each of these rows here for each possible illumination condition on the Earth. And this gives us this transfer matrix. And so the whole story is within this transfer matrix. Any questions about this? Okay, let me go on. So that tells you the likelihood term, like the forward model, the rendering model. Then the other component in the Bayesian estimate of the most probable Earth intensity given the moon intensities is the prior model. What's your prior model for the Earth? So here we have a lot of choices. We could assume, I mean, here's the way that's close. The cheating method would be the following. Let's go up in a satellite, take 100,000 pictures of the Earth with all its different weather conditions, and then assume that the true Earth is one of those 100,000 pictures, that there's 100,000 different configurations of the Earth, and it's going to be one of those. But that would really be cheating. You could hardly call that a camera. That's more like a selection from a prior data set. So, but we want to have some constraints. So we're going to have what I call the round Earth constraint. We assume that the Earth is round and you know where the sun is. And so you'll know that the sunlit part of the Earth is going to have this particular shape, say. But within that, you don't know what it is. And we'll just take random samples from a whole lot of images and do PCA on the results. And that gives us the second row here, which is a modal expansion of the possible components of an Earth image. So at the far left, you have the DC component. And this is basically a Fourier basis expansion in effect. Here's the first component where you have things bright on one side, dark on the other. And then the second component, things dark to the left, bright to the right, and so on for the higher order basis functions. So working in this basis just makes it easier to compute with and also easier to describe a prior. One very simple prior, mathematically simple prior, in terms of these bases, is to assume that each basis is statistically independent of all the other basis functions. And each one is just a Gaussian random variable, mean zero Gaussian random variable, with the variance decreasing for the higher and higher frequencies. So this is very similar to a so-called 1/f prior used in image processing sometimes. And that'll be our prior for the Earth images. And of course, the story is, if you don't use a prior like this and just try to just mathematically invert that transfer matrix, which is the kind of naive thing you would first think of, you'll just get garbage. There are just so many different Earth images that could create a given set of observations. You need to have some regularization that the prior model will bring you. And so the bottom row just shows some random draws then of this prior model of the Earth. Okay, now we get the beauty of Gauss. And this is such old school stuff. I mean, I know each one of you, I haven't even talked with you about your research, but I know for sure that each one of you uses neural networks in your research and just trains things by gradient descent. This is old school stuff, but I think it's important to know and to learn about. We're going to estimate the Earth image as the Bayesian estimate as the product of the likelihood term times the prior term. And because we've set up everything with these Gaussians, we get to reap the benefits of that, which is we get an analytic answer with an analytic description of the mean of this posterior and the variance. So here are the two terms, the likelihood term that I described. It's the this Gaussian where the variable is the difference between the rendered image and the observation. And then the prior term, which is this statistical prior on the different modes of the Earth image. So the product of two Gaussians is another Gaussian, and if you work through the math on that, then you get this straightforward analytic form, which says something really just beautiful, that you take your observations of the moon, and so each of those intensities around the edge of the moon, and you multiply it by this curve, and that'll give you the estimated coefficient for each one of your different Earth modes. I think I have a picture of that. Yeah, so here's a picture of that. So here's the moon. We measure the brightnesses along this path, along this path, along that path, along that path. And then that formula that I just showed you gives you these curves. So for mode 1, you take whatever intensities you measured along that red path on the moon, and you multiply them by this curve here, and then add to it the inner product with this curve here for the observations along the green path, and add to that the product of this curve with the observations along the blue path, and this curve with the observations along the purple path. Sum that all up, and that gives you a number, a scalar. And you take that scalar, you multiply it by this mode basis function, and that's your running reconstruction of the Earth. Do the same thing for the other modes, and you build up a picture of the Earth as estimated by looking at the moon. sounds great, sounds perfect, we're done, right? Except that for the nasty issues of noise. Let's see. So here's a simulation of this. The green is the true amplitudes of the different modes for a particular synthetic image of the Earth, okay? The red is your estimated amplitude of those modes based on simulation of looking at the moon with a particular resolution limit. And we subtracted away the mean just to make it easier. So we're not trying to estimate the mean there. That's why those two curves just disagree so much there. But you can see we do a pretty good job at estimating these mode values. And then finally, it just can't estimate them well. And it gives up. It fails back to the prior. It says, well, I can't really see what that mode's supposed to be. I'm just going to estimate it's probably 0 because that's what the prior tells me it's most likely to be. So that's your best estimate, is the red for the different mode values. And again, this nice Gaussian analytic approach gives you this additional benefit. It shows you the expected noise in your posterior estimate. So these are, okay, horizontally is the mode index, and vertically is the how reliably you can estimate that mode index. And you can see that it has two parts of it. It has one part here where you get more and more uncertain as you get to higher and higher mode values. The fine details are harder to see. And then it just gives up and says, well, it's probably 0, and then the posterior variance goes down. And so actually the peak here shows you where the transition is from estimates being based on actually looking at what's there to estimates being based on what the prior model tells you. So anyway, so if you look at this, you can see it gives you about 7 or 8 modes worth of good data. And you can get the same estimate if you look at these, compare the real and estimated modes here out to about 7 or 8. It's doing a good job, and then it gives up. So what kind of an Earth image can we pull out of 7 or 8 modes worth of the Earth? It's not that good, not that strong. So here's your input Earth image. Here it is projected down to like 30 modes. And here it is projected down to, here's the posterior estimate from the simulation I just showed you with about 7 or 8 modes worth of good data. It's nothing to write home about. It's not that strong. So this is with 0.1% observation noise. And so you'd have to average over a number of pictures to get it down to accurately knowing the intensities to within 1 part in 1,000. But you could do it. And if you're really you average over a lot of them, maybe you could get to 1 part in 10,000 accuracy, maybe. And even so, you don't get that much better an image, and that's because you're limited by the resolution. If you allow yourself a professional telescope, so now I've changed the images on you. Now we're assuming that you can have up to, I think it's, sorry, what is it? Yes, 0.1 arc seconds resolution. So that's a professional telescope. Then you can get an image look like either one of these two. And that's not, that's okay. You could see probably weather patterns. You could probably see continents with an image of that resolution. And then the only frustrating thing is that's not what you could get with a backyard telescope. You'd need to go to an observatory and work with a professional to get an image like that. Okay, so that was kind of disappointing. I wanted better. Actually, recently I've been revisiting this, and I think there might be some hope to try to get higher resolution, but I'd have no results to report on yet. No results on that to report yet, other than to say I haven't given up yet. But I want to tell you about the spin-off from that. So it was sort of funding, and there's a project, a MURI, multi-university research initiative, for looking around the corner. So you look at a wall and you want to see what's going on inside a room, even though you can't see what's there in the room. You can just see the wall. And we used, I got involved in this project, and we used the results of my analysis of the moon for that project of non-light of sight imaging. We would say, okay, assume there's a Gaussian sphere inside the room that you get to look at, and then just use all the same math, the same equations, and came up with pictures of what the multipliers are. So here's another view of it, by the way. This is for a Lambertian sphere, so it's closer than the moon, but it's the same math. And you can have two different flavors of the Lambertian sphere, the pure Lambert and also a very rough one. And then here, these are the multipliers. You take the image that you see of that and multiply by this image, and you get the coefficient for this mode, and you multiply by this image, and you get the coefficients for this mode, and so on. And we applied it to a conference room setting, and you could reconstruct images like this video of someone walking by, or reconstruct this image of the people in a room. So I used it for the first year of this grant, just the exact same equations I had from the moon, but applied to a conference room setting. So that was spin-off number one. Okay, then, but I didn't give up on this problem. So let's look at another way of reconstructing the image of the Earth by looking at the moon. And this is by looking at fuzzy boundaries of cast shadows. And this led to a whole new research direction for my group that we explored. Here's the idea. So in both these issues, the issue that you have to confront is, how do you get an observable brightness difference on the moon resulting from a very, very tiny change in the angle of incidence of the light leaving the Earth? That's the task you have to make an imaging system of this configuration. So for the first thing I just showed you, we relied on just looking at the very edge of the moon where a small change in the input angle might yield a big enough brightness change that you could observe it. Here's a different way to do it, and that is to take advantage of craters on the moon. So here's a drawing. Here's a crater on the moon, and here's the front side toward the Earth, and here's the back side. If you look at the moon, there's going to be cast shadows of those craters. You can see the cast shadows from sunlight if you look at the moon with binoculars or a telescope, but there's going to be the same ones from Earthshine. And there you'll see, that's a condition where you'll see significant intensity change, even from a very small change in angle. So if you sit at the crater here and look back at the Earth, what are you going to see? Well, it's going to look like, here's the Earth, and here's the front of the crater, which is from this point here, which is in full Earthshine. The entire Earth is visible to you from that point on the crater. So from here, the front wall of the crater looks like that on the right, and you can see the full Earth. But if you're at point B or point C, you're in this penumbra of the shadow. You can only, and if you look back from, say, point C and look toward the Earth, this is what you'll see. Then the front wall of the crater is going to be this curve here, and it cuts right through the halfway on the Earth, and you'll only see half of the Earth's intensity, the average of all of the upper half pixels, illuminating you at position C. And so this brightness that reflects back to the Earth will tell you the integral of all the pixels on the Earth from this point and above. And if you're at point D, the brightness there will tell you the integral of all the brightness pixels on the Earth from this point and above, and so forth. So in other words, if you sit on the Earth with a telescope and look at this penumbra of the shadow and record the brightness changes across that penumbra, you'll get a whole set of partial sums of the Earth image intensities. So that seems like that should do it. That should let you back out this partial sum of all the intensities in this direction. And if you make that measurement from a number of different points along the perimeter of the moon again, you'll get partial sums such as shown by these lines here. From one point on the yellow crater, you'll see the partial sum of everything at this line and beyond, or this line and beyond from another point. And so that gives you what we need. It's like now we just have to solve this Sudoku problem of given all those partial sums, what are the brightnesses everywhere? But we know how to do that. That's just linear algebra. So now, again, we're going to look at the edge of the moon, but we're going to look at craters and look at these cast shadows, these penumbras of the cast shadows of craters. So what's going to be our friend? Our friend is going to be a really big crater, because then the throw length of the cast shadow is going to be very long, and the penumbra of the cast shadow is going to be spread out over a large enough distance that we can resolve it with our telescope back on the Earth. And so you want to get a map of the moon, figure out what is the size of all the craters around the edge of the moon that you might be able to use to measure the fuzzy boundaries of the cast shadows of Earthshine. So here's a list of example craters. If you look around, there's going to be enough, the 50 kilometer or 100 kilometer, that might be a reasonable throw length to expect for the shadow. And so, so you can do the calculation of how much resolution you'll get from a given throw length. And the longer the throw length, the higher the resolution. And here are the results of that. So again, here's the ground truth Earth image. This first column here, we're restricted to a backyard telescope. Here I allowed myself 0.33 arc seconds of resolution, which is still feasible, but it's hard. And if you have 50 kilometer cast shadows, then you'll get this top middle image. If you have 100 kilometer cast shadows, so 100 kilometer size craters, then you'll get about 5 pixels of resolution across the Earth's diameter, which looks about like this. And again, if we allow ourselves to go to a professional telescope and get 0.1 arc seconds of resolution, then with a set of 50 kilometer craters, we can get this image. And with a set of 100 kilometer craters, we can get this image, which I would be quite happy with. But again, we're kind of, it's something you could really only do with a professional telescope, and with a backyard telescope. At the very best, you're going to get an image like this, which is not going to be perhaps too exciting. But I should point out, we had really nice spin-off from this approach also. So this led us to so-called the corner camera and other occlusion-based imaging systems. So this thing with the cast shadow of the crater is basically relying on the occlusion to give you the fast change of image intensity with incoming angle that you require to make an imager. But you can use that even in ground-based systems as well. So I just want to go off on a 5 or 10 minute diversion to tell you about these really fun occlusion-based imaging systems on the Earth. We made something that we call the corner camera. And so it requires just 2 things. It requires a ground plane, which we have everywhere, and an occluder. If you, let's see, here's a visualization of how it works. Okay, there we go. So there you can see the shadow moving as I move this light source. And so what's going on? So these points on the ground here, they're integrating the light from everywhere, except they stop integrating from stuff over here when they see the corner. And then so it's an integral of all the light over here and then up to this point here. And it's there's not much sensitivity to changes in the vertical direction, because this occluder is constant in the vertical direction, but there is a lot of sensitivity to the horizontal, as you can see from the edge moving around. So given that so if you look from where I am at this point on the ground, you'll see the integral of all the light falling on that point up until this edge. And so how would you read out from an integrator like this? Well, you differentiate. And so if you differentiate the observed brightness with respect to angle, you'll pull out a 1D image of what's around the corner from this integration effect. And I'm sort of making it all visible with this flashlight here, but the same holds true even for ordinary contrast things. So if I take this thing just without turning on the flashlight and showing it here, there's an invisible change in the brightness on this point here by the fact that I've introduced this contrast element in this part of the scene. And you might ask yourself, well, what is the size of that effect? Well, you can look experimentally and also theoretically, and it's about 1 part in 1,000. So if I put this here, it changes the brightness I observed there by about 1 part in 1,000. And that's invisible to the human eye, but it's perfectly straightforward to calculate from averaging a neighborhood of pixels to give you 1 part in 1,000 intensity resolution. And so, which is to say that in our daily world, there are all these corner structures all over the place. So here's a picture, part of the MIT campus. You can see there in the middle, there's a corner and there's a ground plane. And if we zoom in on that corner, you can see the ground. If you took a video of that, you wouldn't see, it would be very, very boring video. But actually, there would be 1 part in 1,000 intensity differences that were happening based on what was going on around the corner. And let me prove that to you. So we took a camera, look at those. We had 2 people walk around the corner. So one of them is Katie Bauman, who's a faculty member at Caltech now, and the other is now a graduate student at Berkeley. So they're going to walk around. This is totally non-laboratory conditions. There are cars driving by, there's sunlight, but we're going to look at the part of the corner there. And here, let me show you that video, which is the world's most boring video because there are these 1 part in 1,000 intensity differences that you can't see. Here it is. I'm playing it now. Okay, that's the input. And then, but if you just take this, let me show you that multiplier again. We're going to take these pie-shaped wedges from this thing and differentiate them to get, that's our multiplier that tells us, that reads out as a function of angle what the image intensity is. And now we're going to, that gives us a 1D video in a sense. Now we're going to plot the result. Here's angle or space, and here's time. And you can see these traces that appear based on the input that you saw there, which you couldn't see visually, but they're there in the data. So everywhere in the world, around a corner, there are these 1D videos playing that you can read out if you look on the ground. And you might ask, well, what value is a 1D video? They are limited in value. It's not like seeing a 2D video, but you can tell, for example, how fast is the person moving? When are they close to the corner? When are they far away? How many people are there? So here are the answer to those. There's 1 person. Here's another video when there were 2 people moving around, and you can see the 2 tracks. So it's a, I find this delightful just to think that around every corner, if you look at the ground, you could pull out potentially a little picture of what's going on around the corner from this invisible signal, which is accessible with ordinary webcams. So let me just show you, let's see. Here we tried to make it really obvious. So we had bright lights, we had a white sheet here, and you could see these traces, but even under much less constrained conditions, you can still see them. So here, they're walking around in a corner. Here, the camera's over here. This is an indoor scene looking at this point. Here's the video again. Can't see anything, but you can pull out this 1D video from this occlusion-based imaging system and see the result. How might you use this? Well, you could imagine, again, it works outside. You could imagine using it to see if there's a little kid running around the corner toward your automated car or something. So to test this out, we rented a child, well, we borrowed someone's child and had them walk around in a circle. And then we're here around the corner looking at the ground. Here it is, the ground again. Again, you can't see evidence on the ground of them moving, but this is the video playing while they were moving. But we could pull out a trace of the child running around, just looking at this on the sidewalk. So, so again, that's the sort of spin-off from this moon project, was this occlusion-based imager on the Earth. Some limitations of it, let me point out.
Bill, can I quickly ask, actually, can you go back to this video? I feel, is that zoom or, I mean, it seems you can see something changing, right?
Oh, I see.
Especially when you're going backwards and forward in the video, you see that some stuff is changing on the side here. Yeah, when you do this, what you're doing right now.
Yeah. I think it's changing scenes, actually. So let me play it. So now it's playing. And they're all synchronized. So so here's the 1D reconstruction played out. Here's the input video. I mean, what's going on behind the corner. And here's the input video to the algorithm.
And now these pixels at the top did something, right?
I'm sorry, what?
So, some pixels on the top did something right in the corner. Or maybe I'm imagining it, but it might be also that this is compression via Zoom or whatever, right?
I see. Okay. When I scrub it, you do see changes because it's like a different time of day, different cut. Like when we scrub it, like here from there.
Yeah, sure, but that's the whole thing. That's the
yeah.
That's different. But what I'm saying is like it looks like it's kind of synchronized with the walking, but maybe I'm just wrong. Maybe we just imagine.
Well, I mean, it's not an absolute. I mean, they could, if they walk very close to the corner, they will make perhaps a cast shadow that you do see.
Can you go to the kit again when you go to letter?
Yeah, sure.
That one I think was more interesting. Yeah. Yeah, I don't know. It's changing at the top, right? No.
There, it changed.
Yeah.
There, it changed. So I get, yeah, there is some, yeah.
But I understand it's very, very subtle.
Yeah. So limitations, because we assume we don't know what's on the ground, we can't do this with a static scene because then the cast shadow on the ground confounds itself with the reflectance changes on the ground of the dirt on the ground. And so we have to subtract away a mean image or an average image over time. So this then gives us what I call T-Rex vision, like from the film Jurassic Park, the Tyrannosaurus Rex famously couldn't see motion, and so the kids could survive in the car if they just stayed perfectly still. So anyway, we suffer from the same constraint that we can only see things moving around the corner. We can't see things that are static around the corner. But this led to a whole direction of our research group and the collaborators with us of looking at occlusion-based imaging systems. We've had one for an autonomous robot on the far right. If you further assume that you know the exact details of like some plant that's occluding things, you can even pull out a light field. It's a really lousy light field, but you can do it. And we've done that. And anyway, it just led to this nice research area of occlusion-based imaging. And so that's, again, the second spinoff. This last one, I really don't have time to explain much. There's been recent work in the non-light of sight imaging community on modulating lasers and letting the modulated laser light reflect. And it turns out that you get a specular reflection out of this modulation that sees the roughness of the wall at the wavelength of the modulation rather than at the wavelength of the carrier band. So you can see something as being specular, even though to the visible light, it looks very, very rough. And so I was thinking maybe that could be used to get a specular reflection off the moon. And the spinoff from that was that it led me to understand better this form of imaging. Anyway, I'll skip through this, but there's kind of three ways that sunlight might leave a signature in it of a reflection with the surface. So one is the BDRF, and that just tells you brightness is a function of angle, which lets us see things in general. Another is a modulation to the spectrum of the reflected light that tells you the color of things. And there's this new third way of seeing a change in sunlight after a reflection off a surface, and that the modulation structure of the sunlight is going to change as a function of angle. So this is something that I'm hoping to explore. But again, it's a result that fell out of thinking about this problem. So then in conclusion, here are these three methods. Succeeded yet. I still have hope that the diffuse reflection approach will lead to results. And I want to, there's a postdoc coming to my lab later, probably, who's very good in image processing. And I want to perhaps work with her on this project. But what's nice about it is, rather than being the dark side of tenure, this whole thing is actually the bright side of tenure, because it's led to a lot of fruitful research in computational imaging, even though just on this one project, and there's no entity on the planet, no company that's going to let you do something that a university lets you do, which is to say, sure, go work on this problem for 12 years. You might not solve it. I don't care. That's fine. No other structure is going to allow you that freedom to do this, which has led to a lot of benefits for me. And so, it's very much the bright side of tenure, and I will keep you posted as progress continues on this problem. So thanks very much.
Yeah, thanks a lot. Really cool talk. So I guess we can take some questions. So if anybody has some question, feel free to ask. Yeah, just turn on your microphone and speak.
Hi, can I ask something, Matthias?
Yeah, of course. Go ahead.
So in some point you mentioned that you need to move to capture the information,
Yes.
but you need the movement.
Right.
So I was wondering which is the connection with this paper from the Zaragoza group that is non-light of sign imaging using phaser field virtual wave optics.
Right.
And I think that so basically they could find they could reconstruct a part of a scene that is that you cannot see with the reflection of the light with the wall. But as far as I know, they mentioned that the restriction is like it was a lab setup. So I was wondering, like, how do you compare this? Because in your case, you show a video with natural light.
Right. So I showed 3 different methods of doing this non-line of sight imaging. The one that I didn't have time to go into is the third one, and that's the one that is was inspired by the Zaragoza group work that you described. So here's a slide. I assume you mean this group.
Yes.
And yes, this is a picture of their lab equipment. And so what they did requires lasers, but the principle behind it should apply to sunlight as well. And the issue as to for whether or not it will work depends on how much modulation is there in the amplitude of sunlight at various different frequencies that are lower than the visible light frequency. So for example, at a 32 thousandths of a second period, how much modulation is there at that period in sunlight? And I've tried to look for those modulations with short exposures of cameras, and I can't really see that modulation. So it may be that there just isn't enough of that modulation in sunlight to let you do it with this passive system. But definitely with a laser-based system, you can definitely do it. And this was the work done by Velton's group and also in collaboration with the Zaragoza group that you talked about, I think. So that's item number 3. And the other 2 are different methods, and they're not at all restricted to lasers.
Okay, thanks.
Yeah.
There was one question on YouTube. So how does the corner camera method work when you either have poor lighting or when the camera is moving?
Thank you. So, in the we've done it under a variety of different lighting conditions. We've done it in sunlight, in outdoors diffuse light. We've done it indoors with lighting, but there can be lighting conditions where there's not enough light and you just won't see it. That's true. And then when the camera's moving is a harder problem that we haven't addressed too much. In principle, provided you can just register all the images from the moving camera to each other, then you should be okay. Because if you assume that the ground plane is Lambertian and light reflects equally in all directions, then as long as you register them with each other, you should really have the same problem as you do with a camera on a tripod. But just to make our lives easier, we haven't addressed that second problem. We've had our cameras on tripods for all the scenes that we've done so far. But I believe it's feasible to do it even with a moving camera.
But shouldn't it be actually, so the moving camera, I think, is a pretty interesting scenario. So, because I think it should be easier because the real surface is not perfectly diffuse. And let's just say, for the sake of simplicity, we can track the camera, right? We can register everything together.
Yeah.
You should get more information, right? Let's say there's a periodic signal that is, just for sake of simplicity, is perfectly repeating itself. Then you should kind of you should sample the hemisphere, right?
Yeah, good point. In other words, that if you assume that the signal you measure from the ground is a combination of a diffuse plus a specular component, is that what you're saying?
Well, I'm saying, like, it's not going to be perfectly diffuse. So you have a very small part, even on a floor, right? There's a small part of specularity. And let's say I'm just assuming you can pretty much perfectly register the camera motion. You just track it somehow with whatever SLAM method you're using. And let's say the signal is also periodic. Like, I'm talking about, like, the people moving around. Let's say they're moving the circuit perfectly. And that it's in a sense, you could kind of replicate the version where you just have multiple cameras, basically.
Yes, I think that's true. I think I feel like it's always going to be easier on a tripod, but I think you could overcome the restrictions with a moving camera. There's another thing that we've tried also, and that is so the big issue with taking pictures on an uncalibrated ground, just dirt everywhere and stuff, is the fact that you don't know what the ground plane reflectance pattern is. But interestingly, these very low intensity signals from around the corner, they all come in these pie shapes, because you're basically taking an integral of the video that's around the corner. And so the changes that you're interested in are these pie shapes moving around, and the things that you're not interested in have some general configuration. So you could imagine trying to distinguish those two by saying, I only want to look at intensity changes that have this pie-shaped structure, and anything that doesn't have that structure, I assume is not the signal I'm looking for. So that's another, it's again makes the problem harder. It's you can do it. It's harder than if you subtract away an average image, but you can do that. So that would allow you to get a picture of what was around the corner, even in a snapshot, just a one photo.
So maybe I can ask a high-level question. What do you think about generally non-line of sight imaging? What's the future of the field right now?
Yeah, that's a great question. It's one of those things that's kind of great for academia, and I just don't know if there's any real practical value to it. I mean, it's a fun problem to work on, and it's cute when I find it satisfying to feel that there are these images everywhere that we can pull out if we look hard enough. But it's just so much easier to have a mirror in there, or to actually put a camera in there, that it seems, in terms of using it as a practical system to look around a corner, it's hard. To be honest, the corner camera is kind of the most practical direction that we've seen of this work, because it's pretty robust, and you just need to look at the ground. But I don't know. Anyway. I love working on these problems. We haven't yet had the home run that's going to let us see movies by looking at a wall or something.
I mean, it would be cool if you combine with whatever active camera, right? There was a question on YouTube actually, like, can you use audio signals and stuff like this? And do you have any, like, that I feel has more promise in a sense to make it more scalable? You just get so much more signal out of it, right?
Yeah, that's right. I guess I personally am still jazzed about the moon problem, because it would just be so much fun. And you sort of have the time and sort of work to be patient about, setting up carefully and everything. Whereas it, in a kind of public safety thing where you wanted to know if someone was around the corner at night or something, I don't know. I just think other methods might be a better choice than what we can do with non-line of sight imaging so far.
Well, I mean, what's very interesting is if you're thinking about it, maybe not about the corner case, but let's say I don't know, we're very interested in reconstructing rooms and stuff like this, right? You just never can reconstruct everything. So you're always going to have some physical limitations where to move the camera. So you have to, I mean, one way is to do it completely data-driven, right? You just say, oh, whatever you see, you try to infer it. But I think it would be still great to leverage signal like that is non-line of sight, basically.
Yeah. We did, I mean, again, this kind of, it's a real kind of research driver. We did have a thing we call clutter camera, where you just look at a pile of stuff and you'd be surprised in any given pile of stuff, especially around a lab, there are various things that are pretty, that tell you information. They're specularly reflecting or things. And so we've had good results with having very, very uncalibrated clutter cameras for looking back into the room. So yeah, I agree. It is fun. I guess it's such a weak signal that it really forces you to address head on the issue of image priors and scene priors. And it kind of forces you to think hard about those questions, which can also show up in the things you described of just trying to get a 3D reconstruction of your scene. Priors are going to.
I mean, it seems like the priors is the way to go, what people do right now, because it's just so easy with neural networks. You just learn them and, you have some observations. I mean, it's easy, but I mean, the reason why I enjoy this work a lot, what you presented, is like, you're just going to the really extreme, like what's the minimal amount of signal you kind of need, right? That's the interesting piece, right? What can you still like squeeze the last detail out of it?
Yeah.
Are there any other questions?
Hey, I have a question. What's your take like actually on broken hardware? Like we in our lab, like we only work on software right now, and doing like low level vision. But sometimes it feels like, oh, it would be super satisfying, I don't know, to work on a small robot or anything. But like once you go in this direction and do have hardware stuff, it feels like, yeah, things can break and everything like that.
Yes. So sort of at a high level, what are my thoughts about hardware versus software work in computational imaging? Is that?
Yeah, like just like a general feeling, like how often does your hardware actually break? Or I mean, you have hands-on experience with like actually working hardware.
Right. So I'm somewhere in between. We don't make new cameras. I mean, let's see, we use existing cameras to form accidental cameras. But I don't know. There's strong things on both sides. I don't know what to say. I think what's really powerful is to be able to go from one area of that to another. I mean, to go from the theory all the way to the hardware. I think that's really powerful. And there's so many people who are just restricted to one corner that you have a big advantage over them if you can do both strong theory and strong hardware. Then you really win. I don't have the kind of hardware lab that I would like to. Actually, Katie Bauman, my former student who worked on the Event Horizon telescope, she has just started as a faculty member at Caltech. And I was so envious of her wonderful lab. She has a great hardware lab and space. I don't have that, but I could try to fight for it, but I don't have it yet. Anyway, both are fun. And I think being fearless and doing both is really the best.
All right. Thanks. Yeah, I think we are a little bit over time. So really, thanks a lot. I think this is really cool. I'm very happy to hear a talk that is not just about neural networks. I'm very happy that this is not just another architecture. So this is very inspiring. So it's a good intuition for students, I think, to see something what vision is actually about in imaging. So yeah, so thanks a lot. It was really great. I think we're gonna move to the private Zoom. I'm gonna end the stream. So to everybody else, before CVPR, this was our last lecture. Like after CVPR, we will continue. So otherwise, good luck everybody working on this deadline.
Yes, good luck to all. And again, next time I'll hope to see you in person. So Matthias, should I stay on this Zoom?
No, I think Dan, send you another one.